Okay, algorithms. Okay, so the first kind of thing that we need here is I'm going to start writing a little bit smaller letters because I may need to write some equations. So the first one is the parameterized policy. So this is basically going to be done with a network, obviously, and we will call it pi theta. And pi theta is obviously a first given A. So mind you, one kind of interesting kind of point here, the S prime, the state that we will transition in the case of fine-tuning, let's say, a language model is not, we don't have a stochastic transition model there because, you know, the stochasticity, of course, is induced by the fact that we have to have some kind of sampling process. I have a posterior kind of probability distribution. How am I going to sample out of this posterior probability distribution a token? But the moment I have the token in my hands, the S prime is deterministic. I will just attach it to at the end of the previous state. Okay, so I will. So I hope this kind of recognized. So we have some kind of things working for us. Okay, so obviously I forgot the parameter here. Okay, I put the parameter. Sometimes you will see that also. Okay, sometimes you will see that also as pi of s given a comma theta. Okay. Okay, so this kind of parameters, effectively, if I change the parameters from theta 1 and to theta 2, obviously what I'm going to be producing is the pi of theta 1 is different to the pi of theta 2 for obvious reasons. The second one is the objective function. I'm going to call it loss a little bit later, but right now it's called the capital J of pi theta. It's an objective function that is a function of the policy, the parameterized kind of policy. And obviously, if it is objective, I try to maximize it. If I put a minus sign in front of it and I call it a loss, I'm trying to minimize it. Okay. And then the third quantity that I need is someone to guide me in this kind of optimization process. A maximization here will be done with a stochastic gradient ascent or minimization with the stochastic gradient descent. And in order for any of these kind of algorithms to work, then I need the gradient of the policy. And so this is policy gradient. All right. So let's see how it is. Let's see how it is going to be to work. So basically, what we're trying to do here, this is the objective. I forgot to write the objective. So the objective here is going to be equal to max over theta of j of pi of theta. If either write max over theta or max over pi of theta of j pi of theta is the same thing because theta determines a specific posterior probability distribution of the output. Okay. Okay, and of course the policy kind of gradient is going to be used over here. So it's going to be theta k plus 1 is equal to theta in the case of stochastic gradient ascent plus alpha, let's say, gradient over theta of j of pi of theta. So this guy here is called learning rate. Okay, so by the way, I wanted to open a parenthesis kind of here. I remember I was telling you last time about the Bible, right, in reinforcement learning, which is the Saturn's kind of book. The notation is coming from here. However, when it comes to recent kind of algorithms and things like that, the second book I suggested, which was written by the Google engineers, right, the alphabet guys over there, and gals, is really the book to have, okay? And actually go through that in a kind of a line by line because it's actually pretty dense, despite the fact that this, looks like a bit Pythonic. The book I'm referring to is this Foundations of Deep Reinforcement Learning from Laura Grassler and Wang Lung Kang. And this book is obviously available free of charge to you through the NGIT library. I do hope that you did take a look on that kind of book as well, as it has some really good treatment on contrasting the theory we do here in Python. Okay.
Professor, what was the name of the book?
Okay. The book is written over here. Introduction to RL. Foundations of Deep Reinforcement Learning at the end. Saturn is already given. I mean, you need to read Saturn. I mean, the many, especially in the initial stages of the MDP kind of thing, it's and also reinforcement learning, the reinforced kind of algorithm, policy gradient, stuff like that. It's all described there, but it's also described in that kind of book because many of the algorithms in fine tuning is based on policy gradient methods. So this is the book, Foundations of Deep Reinforcement Learning, available free of charge to you. Okay, it's an older book. It's not 2024 or 2025, but sometimes this is better, okay, because it has a little bit more wider scope than the latest and the greatest. Okay. It does have the PPO in there. Okay. All right. Did you write it down or okay? I think it's recorded now, so it's
Yeah, I got it. Thank you.
okay. All right. So in order for us to optimize something, right? So mind you that we need, with this kind of algorithms, this kind of stochastic gradient descent, we need some kind of something to be sort of differentiable, okay? And mind you that when we look at this kind of a chain over here, yes, we have a discrete probability distribution out of which that we sample a token. We take an action. Action for us now is just sampling the posterior, and therefore we have a token in front of us, which is kind of a discrete. But this sampling kind of process is a non-differentiable kind of process. So we need to somehow do what is actually called I'll write it down. I am not going to necessarily expand on this, but the expansion is really well expanded and treated in your website. It's called the log derivative trick, also known as score function or reinforced identity. Okay, so this log derivative trick is as follows. If we have a function f of x and we try to estimate an expectation of x over x, that it is sort of according to this kind of a probability distribution is sampled out of this, it's distributed according to P of x given theta, some kind of parametric probability distribution of a function of x, some f of x. So if we want to calculate this, and we want to compute effectively the gradient of a quantity, and remember all the quantities over here have this kind of inside it, this notion of expected risk, right? So over here we see in supervised learning, if you remember, right? It was basically if we write down the maximum likelihood expression of that of the criterion, let's say the cross entropy, which of course becomes mean square error when the P model is Gaussian. Always we see this kind of expectation, and people refer to this kind of minimizing the expected risk. Okay, and over here we need to minimize some kind of function like this, which has an expectation. We need to obviously take the gradient, calculate the gradient of an expectation. So we are trying to calculate here a gradient of expected the expected value of a function f of x, right? And if you go to the website, we need to do certain kind of steps, which is called this trick that I'm telling you here, the log derivative kind of trick, in order for us to reach the final conclusion. So go through these kind of steps. I think it's pretty straightforward. They're not really anything. But bottom line, if you see this kind of equation 7, effectively we are converting with this kind of transformation the problem of taking the gradient of an expectation into an expectation of a gradient. Okay, which is that quantity over there, the log of the the probability distribution here is going to be computable because it's differentiable. Okay, so this is kind of an important kind of trick, and effectively we are reaching this expression over here. You also see here at the end of this box, which I'm going to write here. So see website for details. Okay. So bottom line, we have now the ability now to write down this for our purposes. Gradient over theta of j of pi of theta is equal to the expectation over trajectories that are generated out of sampling this kind of probability distribution, which is this case is our policy pi of theta. Remember that kind of posterior of the return, the sample return GT, the gradient over theta of log of pi theta, and that's basically it. Okay, so this is basically the log derivative kind of trick, and that allows us to estimate this kind of a gradient that we need in order to adapt this kind of parameters. And the quantity that it is there in the before of this kind of gradient is obviously the return GT that we knew forever from the very beginning of this discussion in the MTP kind of discussion. One thing that we need to pay attention to, however, here is that this the GT of a trajectory is obviously starting from some kind of instant t and referring to a trajectory tau is obviously given by some kind of summation of the discounted returns from the moment that we have t, gamma to the power of over k, gamma to the power of k, r of t plus 1 plus k. Okay. So this is basically our gradient. And now with this kind of in hand, we can actually start thinking about, the optimization kind of algorithm and that it is called reinforce. Okay, so we will, the reinforce kind of algorithm has multiple kind of steps. The first step is to initialize learning rate. Okay, so this is the learning rate alpha in this kind of equation. We define and initialize in it a policy network. For us, it's going to be given. That is, we always symbolize with pi of theta. And then we start generating episodes. Let's say 0 to max episodes. We sample a trajectory. We sample a trajectory tau using pi of theta. We are setting the gradient over theta of j of pi of theta to 0. And for each time that we are going to visit this kind of states inside this trajectory from 0 to capital T minus 1. We compute the return, gt of tau, because we are inside the trajectory tau. And then we update the gradient of the pi of theta to be the previous gradient of ups pi of theta. Hold on a second. Plus gt of tau gradient over theta log pi of theta. Per the previous kind of discussion. And finally, at the end of this kind of for loop, this one are coming together. I have to move a little bit to the left, but these two compute gt of tau, and the gradient is inside that inside this this 40 is equal to 0 kind of group. At the end of this kind of loop, we update our theta per the gradient we just calculated. And we do that for across all episodes. And so we update the theta, and for each update, we are creating, if you like, for each episode, we're creating a new trajectory and so on and so on. So we have lots of samples to generate. This is the reason why this kind of reinforced algorithm is relatively sample inefficient, right? And we obviously will have approaches where it can be converted to a sample efficient kind of algorithm that we will see in a moment, as it has a lot to do with the PPO scheme. Okay. Any questions on this kind of a policy gradient and how we go about doing this kind of updates in our LLMs with this basic reinforced method? Okay, so with that, let's see now what is the next logical kind of thing to do. Okay, I don't have the PPO kind of write up yet done on the website, so I'm going to just basically write everything here and finish with that sort of. So before we kind of get started, one thing that I wanted to mention is this on the value of relative rewards. So this kind of discussion, I think I had this, yeah. So I have this kind of an analogy. So let's assume that you have two students, right? So you have student one that takes, grades like this, whatever, some really high scores. And you have, let's say, student two that has some kind of history of fairly poor grades, and so on, right? And what is actually going to happen here? And let's assume that the teacher is awards, if you like, this grades, and with this kind of grades, the parents is awarding some money. Let's assume that these two students are brothers, and they are sort of going to to a parent to sort of present the grades, and the parent in rewards, giving you a reward that it is actually associated with the grade that he brought up. So obviously, student one will receive a much larger reward than the student two. And however, let's consider something that may actually happen over there. Student 2 suddenly produces a grade which is 80. So we went from an average of 50 to an average of 80. And student 1 kind of continues to be close to the history of grades that he was always kind of brought up. So there are two things that are going to be, if we don't do a change, if you like, this kind of reward, and we always award money based on the grade, absolute kind of grade, we will, there's going to be some kind of unfairness, you can think about it, in a sense that, brother student 2, let's say, improved quite considerably from what we call the baseline. And if we continue to give absolute kind of rewards, obviously give more money to the person who brought back the highest kind of grade, we create some form of kind of unfairness between the two, because obviously the student put quite a lot of effort into presenting and taking a result such as this. So the approach, if you like, in terms of that PPO and others before it kind of brought to the table is to introduce, if you like, a scheme that is actually looks at relative improvement over the baseline. So let me write it down. PPO, another algorithms, reward based on improvement over a baseline. And coming up with a baseline is kind of a problem by itself, because as the grades and semesters go by and so on and so on, you probably also know this from your own kind of experience, that sometimes, we have non-stationary kind of situations going on, and a student 1 in one semester becomes student 2 in a second semester and things like that. And so the baseline has to also be adapted or learned, okay? And so to make sure that we have kind of fairness across the population of just 2 students here, but you can generalize to many more. So basically, bottom line is not only the absolute score, but it's also about how of the improvement relative to the current level that we call here the baseline. Okay, so we are going to call this the score line, this baseline, as also known as a score line, as a value function. Of being in this kind of state, where state is basically the grade that we have now, the history of grades that we have brought up to this moment in time. So we need to learn, and we parameterize this value function typical with letter phi, because it's going to be the job of some other kind of network that we will call, if you like, the critic, to estimate that kind of baseline. And the difference, this relative difference between the immediate kind of reward and the baseline is going to be called an advantage. And advantage is at time t, where the sort of grade was brought up, is going to be denoted by this letter, capital AT. Okay, we have not used capital A, I think, up to this moment in time. So the advantage capital AT is equal to RT minus V phi of ST. So basically this equation means that if for a given state, ST and action, small letter AT, right? If the reward exceeds the critic's expectation, means that the action perform better than predicted. Okay, and of course, if it is lower, then it is underperformed, or and vice versa. Okay, so definitely we see that if it is exactly as predicted, this advantage will be zero, obviously. And what has been found empirically also is that this kind of looking at relative rewards, or what's called the advantage over here, also reduced the variance during training, and therefore it by that also, if you remember behaviors of stochastic gradient sense and things like that that we did much earlier, then it improved the sort of quality of the gradient, which is actually important when you do take actions. Okay, and so effectively we are encouraging actions that have sort of a large advantage and discouraging actions that don't have such a large advantage, okay, relatively speaking. Okay, so that is basically one aspect that I wanted to introduce beforehand with this kind of analogy for us to understand the role of this kind of capital A that will play in the discussion of the PPO. Okay, so PPO is going to be it's kind of an algorithm which is entirely based on this kind of advantage, right? So calculates this. So let me write it down. So PPO calculates the AT, and obviously this A of T, this calculation is going to be plugged in somewhere, right? And this somewhere is what we call the policy gradient loss, and uses it in the policy gradient loss that we defined as L theta is equal some, let's say, summation from t is equal to 0 to capital T log. So I think I had it as, what is it? Log pi of theta at. Okay. So this is basically this kind of loss. We kind of call it that results into, if you like, into new actions that gradually, as the training kind of continues, results into a larger and larger kind of advantage, or a smaller and smaller kind of loss, is called the actor loss. Because this loss is actually used to define actions, therefore we are acting, while there's going to be another loss, which is going to be associated with the estimation of this quantity, the baseline, and this is going to be obviously called the critic kind of loss. Okay, so let's write it kind of down. Okay, so the value function now v phi is is obviously given by, let's say, of S of t is obviously given just like all the previous kind of discussion we had from the MDP kind of days. But over here, we do not have MDP, but we have some form of kind of a Monte Carlo kind of going on. Is expectation over a trajectory that is sampled based on this kind of policy pi of RT plus 1 plus gamma RT plus 2 plus dot 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 plus gamma capital T minus T RT, let's say. This is basically our last reward that we're going to get. And so we are kind of estimating this kind of VT, V5 of ST based on some kind of experiences that we are. And typically what we have done earlier, we are going to be estimating it with some TD temporal kind of difference type of method. Okay, and this is the reason why PPO and temporal difference methods are ultimately kind of linked. And when you study PPO, you have to study beforehand the TD of lambda in general. Okay, so this is basically, there is going to be some kind of a loss, as I said, associated with the estimation of the value function. And this loss is a mean square error loss. It is summation over T of the square difference between the V5 of ST minus the actual return. But obviously the actual return for that specific trajectory, we know. And this is going to be, that is basically going to give us this kind of loss. We try to minimize this loss, therefore minimize the estimate of the value function relative to what value we have actually experienced trajectory from one trajectory to the other. Okay, so this kind of advantage, the advantage A of t is really the most critical kind of quantity for us to that change, if you like, what we knew earlier with TD kind of methods relative to what we see here in this kind of PPO. Okay. We discount it, and actually we have this kind of exponential weighting. We saw exactly the same thing in TD of lambda, so I'm not really going to expand on that. And in terms of kind of an algorithm, if you want to actually draw something that it is, like a pseudo kind of code, we start from some kind of a initialization of pi of theta and v phi, the value, and for let's say some kind of a this is same for loop as we had kind of earlier. So we have episodes, if you like, from episode is equal to 0 to whatever maximum kind of number. Collect a set of trajectories. Let's say tau I, and this is basically a set. That's why I'm using kind of curly brackets by executing policy pi theta. So within this environment, so we have now, we can, I will leave some kind of space over here because I need to add something at the end, which will introduce some kind of complication in the loss formula of PPO because of a concept called important sampling, but I'll come to that. So just like what we did kind of earlier, compute discounted returns. Compute discounted returns to GT to calculate the loss L phi, compute the advantage, AT, based on V phi, on the value estimate, and update policy for the parameters based on the gradient over theta of L theta. And finally, we update value function based on the gradient of the loss associated with the value function estimation. Okay. Okay, so one thing to note, and this is basically why we want to become as sample efficient as possible. So when we are collecting, if you like, data, and we are generating, if you like, a set of trajectories out of this kind of experiences, then probably you notice that as we change the theta over here, the set of trajectories that we generated initially are rapidly becoming, or almost immediately becoming, out of date. Right? So what we are trying to do here is to generate this kind of trajectories, specifically using the the specific episode that generated them. So I will have this kind of E over here for episode, right, as a kind of a policy that we have used at the time. But in order for us to reuse, if you like, this kind of trajectories, we have to do something. Okay? So, and this something means that we have to cannot really update kind of the gradient of the loss and calculate, if you like, by this kind of expectation we saw in the beginning, by assuming a probability distribution that is no longer with us. So we have to do something about it, and I'll describe a concept called importance sampling. So in the space that I left over here, we have reusing these trajectories. With this change, we will be able to reuse the trajectories and do this computations over multiple epochs in a similar way, reusing, if you like, the training data in a very similar way as we have been doing in supervised kind of learning. We are revisiting this kind of data, and we are updating these quantities of interest, losses, and advantage. Okay, and of course the gradients associated with the kind of learning kind of process. But obviously the losses will need to change now. We need to make some kind of a slight change with respect to the loss kind of function. And this will give us introduction to what we'll call ultimately the surrogate loss. So let's look a little bit of the concept of importance sampling. Okay. Okay. So importance sampling. Hold on a second. Are you able to follow what's happening here? I hope you are. I hope you are. So basically, let's open a parenthesis here to understand this. Okay, so in terms of importance sampling, so what is what we will do here, just to derive, if you like, the importance sampling equation, which is basically calculate some expectation of. So let me write it down. calculate an expectation under one distribution that I'm going to define by P of X over here using samples from another Q of X, let's say. So we'll see, how we were actually going to be doing this and what is going to be the formula of that kind of expectation. That is basically the formula that is absorbed inside the PPO loss function. Okay, so let's just look at the discrete kind of case. We can do that continuous later. So by definition, what is the expectation of f of x over, let's say, p of x over p, let's say, is basically summation of p of x, f of x over x. That's a definition of expectation. Okay. Now let's try to multiply and divide by q of x. So what we'll do now here is going to write summation over x, f of x, p of x, divided by q of x times q of x. I haven't really done anything here. So what we have now can do is kind of group the terms a little bit differently. So we have summation over x, p of x divided by q of x, f of x times, times q of x. I hope you recognize that I haven't really done anything here. And therefore, what we see here is the following. The expectation over p of f of x is the expectation over q now of what is my function now? P of x divided by q of x times f of x. That's it. That is basically how important sampling will actually can help us a little bit here, because as you probably heard me suggesting earlier, as I'm actually training, I'm changing the parameters of the network. Therefore, I'm changing the output probability distribution. And out of this kind of output probability distribution, the new output probability distribution, I am actually calculating returns and therefore expectations. And I want to connect the expectations that I'm calculating to expectations that I would have calculated if I stuck to that policy that the trajectories were generated. Okay, so this is basically the reason why the PPO kind of loss function has this kind of a surrogate loss, where instead of P and Q here, we have P theta new and P theta old, okay, where P theta old is the probability distribution that generated the trajectories. And so effectively what we have in the L of theta, with this in mind, considering that we need to reuse the trajectories, training data, multiple times, just like in supervised learning. During the training process, we need to adjust the L theta to account for the fact that the trajectories were generated using an old policy pi theta old. And therefore, what I'm going to do here is to plug into the L of theta that I see over here, the adjustment that will allow me to calculate the L theta using the new policy, the updated policies as the training continues. So L of theta is equal summation over T of pi theta nu divided by pi theta old. That's the Q. And A of T. Now, there was a log, right? There was a log. Now, the log, OpenAI kind of did not include it finally in the final version of the log, was omitted by OpenAI in the final version of PPO. I do not know why, but it was omitted. Okay. So we are going to call this quantity, which of course changing over time, RT of theta. Okay, we're going to call this quantity RT of theta, and so effectively also this RT of theta captures some kind of intuition, how the model changes between, let's say, updates. And so if R is equal to 1, then we have no changes. But typically, obviously, it is not. And so the final loss that we see here is in PPO is summation over T. And over here, I mean, this is basically the only innovation. I mean, all early kind of discussion was already known from actor critic type of methods that preceded kind of PPO. But PPO tried to kind of limit how the policy updates are happening because they didn't want to introduce instability, especially on large kind of models. So what they have done is they have provided an expression like mean of RT of theta, comma, clip of 1 minus epsilon, comma, RT of theta, comma, 1 plus epsilon. And then this is times A of T. Okay. So basically, we constrain the policy updates by constraining this kind of ratio to between 1 minus epsilon by constraining RT of theta to be between 1 minus epsilon and 1 plus epsilon, where 1, as I told you, is no updates. And obviously, the mean here is ensuring that you take the minimum between the original RT of theta and the clipped version. Okay, so that is basically the PPO kind of loss function. Obviously, there are some further terms in the final version of the PPO function that I have not really mentioned. This has to do with some kind of regularization kind of term that is associated with KL divergence and sort of entropy, and entropy measures in the produced probability distributions. But I skipped that for making sure that we kind of gracefully go from the basic kind of actor critic kind of loss and to the PPO loss.